Now let's look closer into the first categories of the pipelined RDT, the go back in. So this is just the sender side, and we'll come to the receiver side in a couple slides. And first thing first, the packet sequence number in go back in. If you recall in RDT 3.0, we only allow one data packet goes in out without being acknowledged, isn't it? And in that case, we just need one bit sequence number to tell the old packet and the new packets apart. But now, go back and being a pipelined RDT, which we allow multiple packets being out in transit without being acknowledged. So your intuition should also tell you that, hey, you need a higher number of sequence numbers to tell all these in-flight packets apart. You are correct, and we now definitely need more, and k here is obviously larger than 1. Okay. Now, having k bits in the packet header, okay, as the sequence number field, then you see the sequence number can range from 0 all the way to 2 to the power of k subtracting 1. And next, in go back in, or generally the pipelined RDT, we do have this thing called the sending window. And the sending window is usually associated with the limit, okay, we call the n, or the sending window size. Okay, so n here is to limit the number of unact packets allowed. Right? In go back in, this is the number of consecutive unact packets allowed. It's also illustrated here. Okay. From the first packet in flight to the last packet in flight, the max range is n. Right? So at any given point in time, we allow only up to n packets being in transit, not yet acknowledged. And so you see here, this thing is also called the sending window, right? And n here is the sending window size. Now let's take a closer look at the plot over here. So each of these slim rectangles are packets. So the green packets are the very early packets that are already sent and already acknowledged. So this is in the middle of the sender transmission, as you see. And yellow packet, starting from here, the send base. So this is the first packet that is being sent out and not yet acknowledged. And there will be a number of these. So yellow ones are the packets already generated and sent, but not yet acknowledged. Okay. Now, depending on the application level source, the message could be large or small. Okay, so this is illustrating a case when the message is not that large, meaning you don't need to generate that many segments at the transport layer to cover the entire message. So potentially, within the limit n, we might have some sequence numbers that allow us to generate packets to send out, but we don't really need them. So the blue ones are usable, but not yet sent. Okay, so essentially, yellow plus the blue ones should be less than n. All right. Now, to indicate the beginning of the usable packet sequence number, we use yet another variable, the next seek number. Right? So, send base, or sometimes I just call it the base, okay, is the base of the sending window. Next seek number is the next available sequence number that we can generate data packet within the window n. All right. And the last one, so these blank ones are simply outside of the window limit, so not usable. All right. And here, let's assume, okay, send base here finally receive an acknowledgement, and it's acknowledged, so we turn this into green. What do we do here? Now this one is green, isn't it? So send base is only to indicate the first unact packet, so we actually need to what? Change it to this packet sequence number, right? as a result, we shift the window and it's beginning from here and include the next blank packet and turn it what? Blue. So the window is actually sliding over by one packet. Okay, so such a window is also called the sliding window mechanism. So when acknowledgement packet is received, you see these yellow packets turning green gradually, okay, and the window sizes is sliding over and then casting more blank packets into blue ones. All right. Just to make sure that it's clear, send base is the variable in go backend sender that always points to the base of the sending window, which means it's always the first yellow packet's sequence number. So the send base will only be changed when the first yellow packet is acknowledged and turned into green. So send base can no longer be pointing to a green packet, and as a result, it needs to be moved to the sequence number of the first yellow packet now. Right? And you see window then here is sliding over by 1. The next seq num is always pointing to the next sequence number in case we need to generate a new data packet. So in this scenario, it's pointing, of course, to the first blue packet that is usable and not yet sent. So because when we get a call from above and if we need to generate a data packet, then we'll turn this blue one into yellow. And the next seq num is going to be shifted over and reassigned to the first blue packet after sending. Right? And we do not shift the window size at all because the send base is not changed and the n here is a constant. But be careful though. There will be scenarios where, hey, all these blue ones are actually yellow, meaning, yeah, the sender does have large message to send and we are actually exhausting the entire window size to send the message already. In that case, the next seq num will be pointing here at a blank packet. Okay, that is the next available sequence number to generate a data packet. But it's not quite yet pointing at the blue one because, yeah, there's no blue packet at all. All right, so next seq num, to be very precise, it's just to point into the first sequence number in case we need to generate another data packet. The rest of the go backend you heard a little bit already about. The ACK, the sender received, is going to be a cumulative ACK. Okay? What it means is that in the sequence number of the cumulative ACK, it indicates all the data packets before this number n are acknowledged. Okay, so all packets before n, including n, are green. All right. Now, if the sender receives duplicate acknowledgements, so hey, ACK n has already been received, but the next moment, another ACK n is received. What does that say? If you recall earlier, yeah, that usually meant, oh, packet n plus 1, there is a gap at the receiver. And receiver does not send acknowledgement up to sequence number n if there is actually any gap before it. Right? So receiving of a duplicate ACK at the sender side indicates, yeah, whatever n is plus 1 is a packet that's missing. Timer. Yeah, there is only one timer for an entire flight of an ACK packet. So it's a timer associated with the base, okay, of the in-flight ACK packet train. Okay, so that is essentially this. Yeah, the oldest in-flight ACK packet is always indicated by the send base. In a way, yeah, there's a timer associated with the send base, essentially. Whenever the send base is changed or whenever the send base is refreshed, we refresh the timer or restart the timer. if it's a bit unfortunate that we do have packet loss such that the timer needs to time out, then we retransmit the entire flight of packet, starting from n all the way to the highest number that's not yet ACK. So that means starting from the send base all the way to the last of the yellow packet. So timeout indicates the entire flight of the yellow packets will be retransmitted.